Okay, so we're on day 3 of optimization, and before we start this video, something that's been on my mind a lot lately is I feel like these videos, especially with math, can be a little mundane after a while. They all kind of start to run together. I do want to let you know that I really do miss having you guys in my classroom. Looking forward to the day, hopefully soon, that we can be back together again. You guys are one of my favorite classes, and just want to throw that out there. That I miss you guys, and I'm looking forward to getting back to you again whenever that might be. Okay. With that being said, let's get to our last day of new lessons this week, which is on optimization. And today's going to be about volume of a square box. Okay, volume of a square box with a given set of constraints. So this goes back to kind of like the introduction video that we had at the start of the week, where we had that hypothetical situation where you're working for a shipping company or whatever, and you wanted to design like the optimal box, right? The optimal amount of stuff or volume that you can fit in it. Okay. Um, so these problems are actually a little bit longer. So what I'm going to do is one example here with you guys, and then on the next video, I'll post a you try where I actually want you guys to try it on your own, and then open up the video when you're ready to check your own work. Okay, so for our first example here, we're going to say, as a manufacturing engineer, you want to design a box having a square base, that's important, and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? Okay, so you can see that you have a constraint, which is your surface area can only be 108 square inches, and you have an optimization, meaning you want to optimize the volume, so you want to find maximum volume. Okay, so a couple key components. By the way, every one of these problems today is going to look the same. It's just different numbers. Key points on today's lesson is you're always going to have a square base, meaning that when you draw your box, your length and your depth, or whatever you want to call that, your length and your width, is always going to be the same, right? Because a square has the same dimensions. So x and x is going to be your base. And then obviously we have some sort of height to the box, right? So if I'm thinking of my two equations that I need to use, a constraint and an optimization equation, we want to optimize the volume. Okay, so volume would be one equation that we need. Volume being length times width times height. Okay, so x times h is x squared times h. That's where that came from. Okay, another equation that we're going to have to use in this problem is surface area. Okay, so to get surface area, I took, and one thing I just wanted to also mention that this box, I don't know if it says in the problem, but every one of these problems is going to have an open top box. So you don't have to worry about the surface area of the top of the box. It looks like it doesn't mention it. Actually, it does mention it, open box. Okay, so you don't have to worry about the surface area of like a lid on top of it or anything. Okay, but we do want to get the surface area of all the other sides of the box. So this base, all right, if we're just looking at the bottom of the box here, if I color that in a little bit darker, that is going to be x times x, that surface area. So x times x is x squared. And we want to add that together with the surface area of all the other sides of the box. So this side would be x times h, that would be the surface area of that side, and actually it would be the same for all four other sides, okay? So x times h, and there's four sides, so 4xh, okay? So these are the two equations that you're going to use all day today, okay? So with that being said, let's slide that first example aside, and let's pull together a little bit of whiteboard work here. So I've got my optimization equation, which means I'm trying to optimize the volume, right? We want to find the maximum volume that you can put in here. And we have a constraint equation saying that we only have a surface area of 108, I think it said square inches, or yeah, square inches to work with. So these are our two equations, okay? So same thing as before. We have an equation in two variables, right? Volume that we're trying to optimize is x squared times h. We want to get this into one variable, okay? So if you look over here, we have an h, obviously. We can write that in terms of x, so that way I can plug it back into this equation. Okay, so if I do that, I get, let me just switch colors here, I get h is equal to 108 minus x squared over 4x. Okay, that's just solving for h. Okay, all right, so let's take that and let's plug it in for h in our optimization equation. So it's the same thing we've been doing all week, it's volume instead of surface area. Okay, so I'm going to write volume is equal to x squared, and instead of h, I'll write 108 minus x squared over 4x. Okay, because that's what h is. Okay, so let's go through, and before we take the derivative, because remember, we want to find the critical point of this to find we're at our maximum. Before we do that, though, let's simplify this. All right, so we're going to say volume is equal to 108 x squared minus x to the fourth all over 4x. Okay, so all I did was distribute this x squared to the numerator. Okay, so we haven't taken the derivative yet. All we've been doing is simplifying it. At this point, we can probably still simplify this even more before we start taking the derivative to help ourselves. So let's do this. Let's split this up into two fractions. So I have 108 divided by 4, which is going to be 27. X to the second minus x to the first is just x. Remember, we subtract our exponents when we're dividing. Minus, what is this, x to the fourth on top? So this would be 1/4 x to the third, right? Because 4 minus 1 gets me to 3. I'm just subtracting my exponents. Okay, so again, just to backtrack, I divided 108 by 4 to get 27. I divided 1 by 4 to get 1/4. I just split my fraction up. This is going to help me take the derivative, because taking the derivative of this is quicker and easier than taking the derivative of this, right? The first one would require us to use quotient rule, and we don't have to use that if we don't want to. Okay, so let's find the critical point. So let's set the derivative equal to 0. So I'm going to say 0 equals 27 minus 3/4 x to the second. Okay, so what I did here is I took the derivative. Hopefully I didn't lose anyone there. This is the simplified equation. This is the derivative. I'm setting it equal to 0. Okay, all I have to do now is solve for x. So I'm going to say negative 27 equals negative 3 over 4x squared. Okay, so just keep working through here. You'd want to multiply both sides by 4, and then you'd want to divide by negative 3. Another way you could do that is just multiply by the reciprocal, right? So that cancels this whole side out, multiply by the reciprocal, and you end up getting 36 is equal to x squared. Okay, and obviously when you take the square root of that, you get x equals 6. Okay, all right. So how does this help us? This gives us the dimensions of x. So if I bring back our drawing here, right, we've got x. Told us that this should be 6, this should be 6. Now we just have to find what our height should be. Okay, so to find that, what I'm going to do is going to go back up to my height equation, all the way back up to my first equation, and I'm going to plug in 6. So I'm going to say h equals 108 minus 6 squared all over 4 times 6. And when you do that, when you work that out in your calculator, you get h equals 3. Okay, so the final dimensions of this box, okay, to get optimal volume would be 6 by 6 by 3. Okay, so this would be your final answer. Okay, so what I'll do next is I'll place a U-try here. I'll let you guys write this down in your notes. I'll stop the video And then on the second video for today, I'll work out the U-try so you can check your work after you try it on your own. Okay? Let me just give you a clear background here so I can read it a little better. Okay, it says the dimensions of a box with a square base. It should say open top. An open top box with a square base has a surface area of, let's change this to 48 square inches. I do that just because I want the numbers to come out a little bit cleaner. And it says, what are the dimensions that will produce maximum volume? Okay, square base, open top, surface area of 48 inches. What dimensions will produce maximum volume? Please try it on your own. Even if you think you can only get halfway through it, go halfway through it, stop, and then go to my second video to watch for the solution.